Hello, everybody. If you remember, we already started determinants on Monday, and today uh, we will give a few more properties concerning determinants because we already talked about the definition of a determinant. How can we find the determinant of a matrix? We already talked about these facts, but today we will talk about a few more properties. Then we will start vector spaces. Before starting the slides, please note that for the determinants, you are always working with the square matrices, because if your matrix is not a square matrix, then finding a determinant is not possible. So always keep in your mind that in determinants, you are always having a square matrix. Okay, let me share my screen. I think we stopped in this theorem, but let me make it single page first. Oh, it's already single page. Oops. Where did you go? Okay. So if you remember, we gave the definition of a determinant by using this formula, but we said this is just given with respect to first row, but you can always find the determinant with respect to any row and any column. Let me put myself here. So you can use any row or any column to find a determinant. You will decide that, but I told you wherever you see more zeros, you can choose that row or that column. Also, you can use the cofactor expansion. This, if you are gonna find a determinant with respect to any row, then you have to use this formula, or if you will find a determinant with respect to a column, then you have to use this formula. And theseCij's are the cofactors, and we talked about them. They are found by using these submatrices. But the most important thing here is whatever your matrix is, the size is not important. It just has to be square, but always you have to make a sign pattern here. You have to start with plus. In any row or in any column, you have to just go alternatively, plus, minus, plus, minus, plus, minus, plus, minus, plus, minus. And if you can make this sign pattern, then you can pick any row or any column to find a determinant. Then, for example, if you choose the first row, you have to go like plus 3 times, cover up the corresponding column and row, then find the determinant of that submatrix, and then go here minus 5 times, cover up the corresponding column and the row, then find the determinant of the left 2 by 2, again submatrix, and then lastly plus minus 2 times, cover up the column and row, find the determinant of this submatrix. So that was the formula for the determinants. We talked about them, but already if you have a diagonal matrix, upper triangular or lower triangular matrix, then defining the determinant is much easier, because you have to just multiply the diagonal entries. This will give you the determinant. These are the easy cases and special matrices. Also, we talked about if you apply some row operations to your matrix, does the determinant value change? Yes, the determinant value of the new matrix will depend on your row operation. If you are using a row replacement, it's not going to change. If you are using interchangement, I mean, if you are switching 2 rows, then the determinant will take a minus in front of it. Or if you just scale a row, then the determinant of the new matrix will be the k times determinant of the original matrix, and this k will be your scalar actually, and we gave some examples here. And I think lastly we stop here. This is another property of the determinant. If you have 2 square matrices and if you want to find the determinant of their product, this is a very useful formula, because determinant A times B is always given as the product of determinants, determinant A times determinant B. So in another words, determinant is multiplicative. you can always separate them. But you can't say the same thing for the addition operation. I mean, determinant of a plus b will not be equal to determinant a plus determinant b. I mean, it's not always equal. You might, of course, find some matrices which the equality holds, but it's not the general case. And also by using this useful formula, actually, we can solve this example. If A and B are square matrices and A times B invertible, then we can always prove that A and B matrices are both invertible, because it's coming from this formula. If you remember, for determinants, we said determinant is very useful function because by using the determinants, we can decide if a given matrix is invertible or not. Actually, this is the basic reason why we learn determinants, because in order to say that a matrix is invertible, either you have to apply row operations and you have to prove that your matrix is row equivalent to identity matrix, or, and this is a long process, or you can immediately just check the determinant of the matrix, and if it's non-zero, then you can say your matrix is invertible. So here, I will use that fact. If A times B is invertible, then the determinant of this product should be non-zero. And on the other hand, from this theorem, I know that this determinant will be equal to the product of determinants. So if this is non-zero, by this equality, these both values shouldn't be zero, because if you have a non-zero value here in real number system, these numbers cannot be zero. So which means that they are separately non-zero, or these matrices are both invertible. Okay. Another important result is, of course, we are always talking about the square matrices. Determinant of the matrix A will always be equivalent to the determinant of A transpose. This is a very important theorem, because sometimes it might be difficult to work with the matrix A, but instead you can just take the transpose, and it might be much easier to work with the transpose, and you can find the determinant, and then you can go back. Since they are equal, you can find already you can find the determinant of A. So you can see this here easily. If your A is a square matrix here, 2 by 2 matrix, the determinant will be -1 times -2 minus 2 times 1. So it will be 0. Look at the determinant of A transpose. This will be -1 times -2 minus 1 times 2, again 0. So they are equal. Or for 3 by 3 case, how can you find the determinant of this matrix? You can use any row or any column, but I think the first column has more zeros, so you can use that just first row, or you can use the you can use the first column, but also you can use the first row here. Actually, to be honest, I am using the first row because it's always standard. I'm just using plus minus plus pattern here, and I'm just writing 1 times the determinant of this submatrix, which will be this, then minus 0 times, I don't care this part because this is already 0, and then plus 2 times the determinant of this matrix, which is coming also 0, and the determinant is -3. And if you look at A transpose, the transpose will be this. Again, if you use the first row here, you will get 1 times the determinant of this submatrix, and I will get -3. You don't need to go ahead because you are already having 0 entries here. So as you see, these determinants are same. Okay. I think we talked about this example on Monday. Now in this corollary, we give 2 facts. We will say in your matrix, if you have 2 same rows or 2 same columns, automatically your determinant will be 0. Okay, why? Because if you have, for example, two same rows, you can apply the row replacement, right? You can just multiply one of these rows by -1 and add it to the other one. Since they are same, you will get completely 0 row somewhere. Then since row replacement doesn't change the determinant value, the determinant of this new matrix will be 0 since you have completely 0 row, and this will be equivalent to the determinant of the original matrix. So in other words, again, if you have same columns or same rows, the determinant will be 0. The other fact is, in your matrix, if you can take any row or any column to the parentheses of a scalar, then you can always put the scalar outside in this way. Here in the second row, k is the common factor, so you can just take the parentheses of k here. You can write this in this way, or you can say the determinant of this matrix will be equivalent to k times the determinant of this matrix. For example, here, look at this first row. You have 2, 4. In other words, 2 is the common factor. You can take the parentheses of 2 here. This will be 1, this will be 2, and you can pull this 2 outside, and this determinant will be equal to 2 times this determinant of this matrix. So these are the common facts that we need to use in determinants. I think, yeah, we gave all the properties of the determinants, but what's the application of determinant? Again, why do we need to learn determinants? The first reason is, by looking at the determinant of a matrix, as I said, you can decide if the matrix is invertible or not, because if the determinant is non-zero, then your matrix will be invertible. And the second application is, again, just in the first week of the classes, we started linear algebra by looking at a system of linear equations, ax equals b. Of course, here, your coefficient matrix A can be anything. It doesn't have to be a square matrix. But if it's a square matrix, and if it's invertible, there is a way to find the solution. I mean, let me check here. Did I write AX? For example, think about this system, not this system, but just think about there is an A matrix here, and this is the unknown matrix X, and the right-hand side is B, okay? AX equals B. If this A matrix is a square matrix and invertible matrix, you can always multiply both sides by the inverse of this matrix to find the solution set, because this part will give you the identity matrix, and you will get this unknown X will be A inverse times this vector. This is a way to find the solution set, but what happens if your coefficient matrix is large enough? I mean, then finding the inverse can't be easy. Then in that case, we can use another method. We will call it Cramer's rule to find the solution. Instead of finding the inverse, we can use determinant here. This is another application. So if you have a system, linear system AX equals B to solve, and if your matrix A is invertible or the determinant of this matrix is non-zero, then we can always apply Cramer's rule. Cramer's rule say, by using this rule, actually, we can find these unknown entries, x1, x2, depending on the unknown vectors. We can always find these unknowns by using determinants, but here, okay, A refers to the coefficient matrix in your system of linear equations, AX equals B. This part is easy, but what's this AIB here? Actually, AIB will be, for example, if you are trying to find the first entry in your unknown, I mean, if you are trying to find x1, then in your coefficient matrix, you will replace the first column with this constant vector. So you're gonna just remove this first column. Instead of this column, you will put this here. It will be 2, 5, and you will keep the second column. This will be the new matrix, this AIB, or in this case, since you are finding x1, this will be A1B, okay? And you will find the determinant of this new matrix, and the first unknown, for example, x1 will be determinant of this new matrix over determinant of A, which is your already coefficient matrix. And you will do the same thing for the second unknown. To find x2 here, you need to find A2B. What's A2B? In your coefficient matrix, since you are looking for the second unknown, you will replace the second column with this constant vector. You are going to remove it. Instead, you will write here 2, 5, and you will keep the first column. And this will be your new matrix AIB or A2B, and you will find the determinant of this matrix, and you will divide it by the determinant of your original matrix. It will give you the second unknown. As you see, this is very easy, very clear. So in the example, we will understand much better. So in this Cramer's rule, you have two equations, two unknowns, okay? We know how to convert this system into a matrix notation. We can always write AX equals B. So here your coefficient matrix will be 1, 2, minus 2, 3, this, an unknown vector x1, x2, and the right-hand side, the constant matrix will be 2, 5. Okay, I want to solve this system and I want to find x1 and x2. Here, to find x1, I will write the formula here, determinant A1 over determinant of A. So no matter what entry you are finding here, you will always find the determinant of A. So it would be wise to calculate the determinant of your coefficient matrix, and you have to know that somewhere because you are going to use it for both unknowns here. So the determinant of A here, we can calculate 1 times 3 minus 2 times 2. So this will be 7. And my determinant will be 7. I'm just writing this as the denominator. What's determinant of A1? What's A1 here? A1 will be, okay, since you are trying to find the first unknown here, you will just replace the first column with this constant matrix, a constant vector. So instead of 1 minus 2, I'm writing here 2, 5. And the second column will be same. So find the determinant of new matrix, and this will be minus 4. And directly you find x1 here. And similarly, to find x2, go to the coefficient matrix and replace the second column with this constant vector. Then instead of 2, 3, now you are going to write 2, 5 here, as you see, and find the determinant of this matrix, which will be 9. So this gives me the second unknown, x2. So I can now write the solution set in this way. As you see, it's very trivial. So for any invertible A matrix, but that is the requirement, again, as I said, because if A is not invertible, then determinant will be 0, and you can't use these fractions here. They will not be sensible, at least. So A has to be invertible matrix. Then to find this AIB, you have to replace the ith column with this constant vector B, okay? And you have to obtain this new matrix here, and you will find the determinant of this new matrix as the denominator. And the unique solution will be given in this way. All right. And actually here, we gave the example on 2 by 2 case, but this method works for every invertible coefficient matrix. So even if you have 5 equations, 5 unknowns, still this method will work. Then you will have x1, x2, x3, blah, blah, x5. And for each case, you have to find these matrices here. That's the only difference. Okay, and I guess this will be the last definition of determinants. So for an invertible matrix, you can always define the adjugate of this matrix. What's the adjugate? We will denote adjugate of a matrix by this edge ADJ. Sometimes we say also adjoint, but sometimes we say adjugate. They are both same things. And this matrix is given as a transpose of this cofactor matrix. If you remember, we were finding these cofactors Cij by using this determinant formula, and this is called the ijth cofactor. Actually, we mean here, if you want to find Cij, for example, let's say C11, then you will go to here in your matrix A, for example, here, you will go to the first entry and you will just cover up the first corresponding column and row, and since you are here in the lowercase a11, or your I is 1 and j is 1, then this constant will be minus 1 to the power 1 plus 1, so this will be positive. And the determinant of capital Aij, so this Aij's will be actually the submatrices, because you are going this entry, cover up the corresponding column and row. Aij or A11 will be this submatrix, and you need to find the determinant of this matrix. So actually we already gave the definition of these cofactors, and the adjugate matrix is defined as the transpose of this the matrix of these cofactors. And by using the adjugate matrix, we can also find the inverse of the matrix, if it's invertible. So the inverse of this matrix is defined as 1 over determinant of A times the adjugate of A. As an example, of course, it's a long process. I generally don't prefer to use this method unless I'm told to use it. So this is a long process. If in the exams or quizzes, if we don't specify that, please use the adjugate of the matrix to find the inverse. You don't have to use this formula, but it's good to know. So for a given matrix A, this is a 3 by 3 matrix, as you see. If you want to find the adjugate, what can we do? Again, if you can't remember this formula, you always have the standard method to find the inverse. You have to use some row operations, or in another words, we are saying Gaussian elimination, and you have to row reduce your matrix A into an identity matrix. Then we were writing A dash lines I, then we are applying row operations to get something like I, the identity matrix, dash lines, A inverse. This is already the standard method, but this adjugate method, or finding the adjugate, can be another method to find the inverse. For example, here, to find this A inverse, you need adjugate, which means that you need these cofactors, Cij's. But before that, you have to find the determinant of these capital Aij's. So for example, A11 will be, go to the first entry, cover up the corresponding column and row, and A11 will be this submatrix, and the determinant of this matrix will be minus 8. Similarly, for A12, go to the entry A12, lowercase A12, this is this, minus 2, and cover up the corresponding column and row. Then the left matrix, this capital A12 will be 0, 0, minus 1, 4, and the determinant will be found like that. And similarly, you will find all the capital A matrices, the determinant of these submatrices. And by using them, now you can calculate these cofactors. For example, C11 will be minus 1 to the power 1 plus 1 determinant of capital A11, which is this. And similarly for C12, you are applying the definition, you're getting these values, and you will write them in a matrix, but don't forget that the aggregate matrix will be the transpose of these cofactor matrix. So first, you will write the cofactor matrix, but then you will take its transpose to find the aggregate matrix. For example, here, normally the cofactor matrix will be found like that, but the aggregate will be the transpose of this matrix. So you need to find the transpose of this, which will be this last matrix. And this is the aggregate matrix. Still, I'm not done. In order to find the inverse of A, I have to divide this aggregate by the determinant of A. How will I find the determinant of A? Look at this matrix. Actually, you can again use any row or any column to find the determinant, but since I have 2 zeros here, I can use the second row, but you have to remember the sign pattern. So with respect to this sign pattern, I have to start with plus here, the left corner, plus minus plus, then similarly, plus minus plus, minus plus minus, plus minus plus. Since I'm going to use the second row, this will be my sign pattern, which means that minus 1 or minus, go to your matrix A, minus 0 times the submatrix, cover up the corresponding column and row, the determinant of the submatrix, but I don't care because this is 0. So I started with minus, then plus minus 2 times, cover up the corresponding column and row, then I will be left with 1 minus 3 minus 1, 4. This is the submatrix. So I have to find the determinant of this matrix. And lastly, I have to put a minus, but my entry is 0. I don't care what it is. So here automatically I will obtain my determinant minus 2. And the inverse will be, with respect to this formula, will be 1 over determinant times the aggregate matrix, which will be actually this matrix. It's a bit long process, but if you can't row reduce your matrix, you can always use this method as well. Okay. Also, in terms of determinants, there are some geometrical applications. What we mean by the geometrical application, determinants are used to find the areas and volumes of some regions in R2 or R3 or higher dimension. Also, determinants are used with the linear operators. How will we do it? Actually, let's see firstly in an example. Let's take this A matrix as a square matrix, which is given like A0, 0B, and define a linear operator T by using this matrix A. Actually, from here, we already see that A is the standard matrix of my transformation. Okay, and of course, this is clear that this transformation is defined in R2. And the question is, how does this transformation change the area of the original region? Okay, so here we say, for example, take an area which is a square determined by these vectors E1 and E2. So take this square in R2 and apply T, this linear transformation, on this region. And what kind of region you will find? So after the application of T, what's the image of this square, in other words? We can see this by using an explicit formula for T, because we know the definition of T here. Tx is given like Ax, so I know what's A, and this is unknown vector. If I just multiply them, I will get an explicit formula for my linear transformation. So T will carry all the vectors x1, x2 to another vector in R2, which is given ax1, bx2. Okay, so here with respect to this formula, what happens to my square under this transformation? Just look at the basic vectors e1 and e2 because your square is determined with these vectors. If you look at e1, which is given like 1, 0, the image of 1, 0 under t will be a0. Okay, so this point or this vector is taken to this vector a0, which is this. And a doesn't have to be 1 here because we just take them non-zero constants and actually assume that a and b are not 0. That would be better. On the other hand, the image of 0, 1, e2 will be, with respect to, again, this formula, 0b, which is this vector. So again, since a, b are just arbitrary constants and they don't have to be same, in more general case, this square, the image of this square will be actually this rectangle. So my t just took a square and it converted this square into a rectangle. But what about the areas? Is there any connection between the areas of the square and this rectangle? The original area of this square will be 1, and the area of new region will be a times b. So the question is there any connection between these areas? From here, while the first one was 1, now the second one is a times b. It's not that easy to see, but actually the answer is yes, because the connection between these areas will come by using the determinant. And we will give this in this theorem for an n by n matrix. And this assume that this matrix is the standard matrix of this linear transformation T, and take a region in Rn, let's call it like S, and in this case, Rs will be this square. And in special case, if your n is 2, I mean, if you are working in R2 like that, then in R2, you always talk about the area. Then the area of the image of your region S under this T will be equal to the determinant, the absolute value of this determinant of A, which is the standard matrix of T, times the area of your original region. So actually, if you look at this example, this is the area of the original region S. Area of S is 1, and the area of TS is A times B. So A times B equal 1 times what? A times B, right? So here actually, what's the determinant of this matrix? A times B. So as you see, this determinant is coming here as a factor, as a scalar. And but you have to be careful. The determinant of a matrix can always be negative too. But since you are finding here the area and it can't be negative, don't forget to take the absolute value of this determinant value. So in other words, in R2, you are finding the area, and the area of the image under T will be determinant of the standard matrix of T times the area of the original region. Just don't forget again to put these absolute values. And in R3, in space, we always talk about the volume. So the volume of the image of your region will be just the product of the determinant of A. Again, this part doesn't change, the absolute value of the determinant time the volume of the original region. Okay? So as you see, these formulas are also very useful. Also, as a geometrical application, in R3, we use the determinants to find the volume of parallel pipes. So for example, here in the question, we say find the volume of the parallel pipe with which is actually determined with these three vectors. So we just specify this parallel pipe with one vertex at the origin, and the other vertices will be at these points, okay? So my parallel pipe will be determined with these three vectors, and in order to find the volume of a parallel pipe, we will always write these vectors as the column of a matrix, and the determinant of this matrix will give us the volume of the parallel pipes. So these are the vectors given in this question, or these are the vectors which determine my parallel pipe. So write them as the columns of this matrix and calculate its determinant. But of course, its determinant, for example, coming -2, but you are finding the volume, okay? It can't be negative. Don't forget to take the absolute value here. And as you see, the result has to be positive. All right, so I think let me check, we are done with the determinants. Yes. Let me check what time is it. Still we have time. We can start the vector spaces. So again, we finished determinant section. For the determinants, what do we have to know? We have to know how to calculate the determinant of a matrix. We have to know the properties of the determinants, how we apply the determinant as to the product of two matrices or the addition of two matrices. Also, what are the applications of determinant? Determinant can be used to solve system of linear equations by using the Cramer's rule. But in order to use the Cramer's rule, your determinant of your coefficient matrix has to be non-zero, or your coefficient matrix has to be invertible. And also, you can use determinant to find the inverse of a matrix by using the adjugate matrix. And lastly, as a geometrical application, you can always use the determinant to find the volume of a parallel pipe, or the determinant will come to the picture if you are using a linear transformation. I mean, if you have a region in your hand which has some area or volume, and if you are applying a linear transformation, then under this linear transformation, this original region will change for sure, and now you are trying to find what's the relation between the original region and the image region. I mean, is there any connection between their areas or between their volumes? And the answer is yes. This connection will come by using the determinant, okay? So this is the short summary of the determinant section, but I think determinants are trivial enough because you are mostly making some calculations there. But still, if you have any trouble, you can always ask, okay? You can always send me email and ask your questions. All right. And with the fourth chapter, we are starting the vector spaces and subspaces. And actually after now, we will always work with the vector spaces, and we will give some special vector spaces. Of course, still we are working with the matrices or linear transformations. After defining the vector spaces, we will talk about the domain of a matrix, the kernel of a matrix, the null space of a matrix, or the image of a matrix, the column space of a matrix. They will be all special subspaces. And after now, probably until the end of the semester, we will be working with the subspaces, vector space subject. So we have to understand what a vector space is. Actually, up to now, we have been working already with the vector spaces, but we still don't know what the definition is. A vector space, as you see from this definition, a vector space, or we call it as a linear space. A vector space will be a set on which you define an addition and scalar multiplication. And with respect to addition and scalar multiplication, your vector space has to satisfy these 10 axioms. These are the famous 10 axioms. If a set V satisfies these 10 axioms with respect to the addition property and scaling property, then this set will be called a vector space. And what are these properties? First of all, vector space can be defined also on the complex numbers, but in this class, we will work with real numbers, so we will always say a real vector space. So we said in order to define a vector space, you have to give an addition and multiplication, scalar multiplication operations. And with respect to your space, these operations can change. For example, for the addition property, so you have a kind of addition operation in your hand defined in this space, in this set V. First of all, in order to say that a set is a vector space, if you take any two vectors in this set, their sum has to be there. And if you take any vectors, their sum should be commutative. You can always change the order. Or if you take three vectors in this set, then putting the parentheses shouldn't change anything. I mean, you can put these parentheses anywhere you want. And in your set V, there should be a zero vector, which is not effective with respect to this addition operation. In other words, if you add zero vector to your any arbitrary vector, it shouldn't change the result. Also, for every u, there should be a multiplicative inverse for your vector. I mean, if you have a u, then the multiplicative inverse is shown by minus u because their sum should give you this ineffective term 0. These 5 axioms here are the addition axioms, okay? So your set V should satisfy these addition properties, but besides, it has to satisfy these scaling properties, which are, for example, if you take any vector u from your set, and if you multiply your vector with a scalar c, c is any constant in R, then this niv vector should be in your set. Or if you take two vectors from in your set and a scalar from R, then c times in parentheses u plus v can be written as c times u plus c times v. In other words, you can distribute the c into this sum. And you can say the same thing for the scalars. If you take two scalars here, then if you put the parentheses for the sum of these scalars, now in this case, you can distribute this vector into this sum. And again, for two scalars, if you put parentheses in this way, for the product of these scalar and vector, you can always change the place of your parentheses, and you can put it in this way. And for any vector u, there should be a one term in your set, and if you multiply your vector u by 1, then you should get the same thing. I mean, in another words, probably I stated this a bit incorrectly. So if you take any vector u and a scalar, let's say, a scalar 1 from R, but in this case, your scalar is just 1. And if you multiply your vector u by this 1, then you should get the same thing. And this vector, again, in this set V. And these are the scaling properties. And again, if your set V satisfies these 10 axioms, V is called a vector space or a linear space. And actually, as I said already, we have been working on some vector spaces since the beginning of the semester, but we didn't notice, we didn't know the definition. These are already the vector spaces, R, R2, R3, and in general case, Rn will be the most famous vector space actually, because in Rn, you can always define the addition and scalar multiplication by using the vector operations. For example, addition will be the usual plus operation. If you take two vectors, x, y, the plus will refer to x plus y, means just sum all the corresponding entries, x1 plus y1, comma, x2 plus y2, comma, blah, blah, n plus yn, for example. And the scalar multiplication will be, if you take a vector x, it's an n tuple, then c times x will be c times x1 plus c times x1, comma, c times x2, comma, blah, blah, c times xn. So these are your operations, and with respect to these operations, Rn will be a vector space. Or we can say, think about the space of sequences here. And can you define an addition and scalar multiplication on this vector space? Yes, actually the addition can be defined like this is your sequence and this is another sequence. When you sum two sequences, it means that again, sum term by term. Scalar multiplication, D is a scalar and an is your sequence. Again, an means a1, a2, a3, blah, blah, blah. And you are just multiplying D with every term in your sequence, and you will get this sequence here. And with respect to these operations, the space of real sequences will be a vector space. And in this space, the zero vector or the zero sequence will be given with these zeros. So I'm not sure what time is it. I think I have to, yeah, I have to stop, I think. So we will continue with the vector space operations, and we will define some spatial subspaces and on Friday, okay? Let me stop sharing and take care. See you on Friday.